Okay, so let's start with the first of the planar geometry problems. And this one's going to be the easiest. This one you just kind of need to know a definition. So let's say we have a 2-inch thick wall, and we know that there is a heat flux across said wall, which we'll call Q, and it's 15 watts per meter squared. And we also are told the temperature drop across, well, let me usually draw like this. Temperature drop across said wall is equal to 15 degrees Celsius. And we want to know what is thermal conductivity of, that's not a Y, silly me, conductivity of the wall material. It's probably spelled right. It's late. Okay, anyways. So here, you're probably screaming it at me through the iPad. We just need to know Fourier's law. And Fourier's law is a empirically derived thing, and it says that the heat flux is, it's proportional to a drop in temperature, and we know that we can equate these two by just having this constant that we call K. Well, actually, hold on. This is not dt. This would be, oh, I was actually a little bit wrong here. This would be dt dx. So let's call this delta t over delta L in our case. Okay, and so here we can just rewrite this as K, well, yeah, this would just be K delta T over L, because the change in length here is just the length. And if we want to solve for K, this can become K equals QL over delta T, which equals, let's go into SI units. So 2 inches, an inch is not in SI units. In SI units, we want meters. So if you do the conversion, you get something like that, about a 20th of a meter. And then this is in SI units. Let's go ahead and keep the units. 15 watts per meter squared, 0.0508 meters, and over our temperature drop. Okay, and so now I don't have a calculator, but I have a phone. Let's see what our result is. So let's see, 15 divided by 15. You don't even need a calculator. You get 0.0508 for our K. And the units of K are watts per meter Kelvin. It's just meter, right? It's not meter squared. I want to make sure I don't get this wrong. Yeah, it's energy per time per length per degree temperature. So, and a watt is a joule per second. So that is our unit. Okay, and this is just the relatively trivial problem, but this is adopted from something I saw. So, yeah, no Fourier's law. Fourier's law. Okay, this is problem 10.1 out of the book. So, a well-insulated box loses heat to the ambient temperature only through a single glass pane window. We'll call this our window. There's a box like that or something. Area is 1 meter cubed, or squared. Its thickness 0.5 centimeters, or 0.005 meters. The ambient temperature medium is 10 degrees Celsius. We'll call that temperature ambient. The the external heat transfer is 10 watts per meter squared Kelvin. The interior of the box is 25 degrees Celsius, and it's well mixed. So so basically this is just 25 degrees right here. That whole surface is just the temperature of the box. Oh yeah, it says that too. And then and you have 15 cents per kilowatt hour. What is the annual cost of maintaining the system? And they give us a thermal conductivity of the glass. Okay, so let's see. If they want the cost, we're going to need to know how much heat we're losing, because the heat you're losing, if you want to maintain the temperature, the heat you're losing, you're going to want to make equal to, whatever you're heating it up. And then, after we get this, we can just convert this using the dollar per kilowatt hour. So how can we find the heat losing? Well, you can calculate the heat leaving a surface or the heat flux off a surface using Fourier's law. So if we want to calculate the total heat flux, that would be K times the area times delta T. Or actually, since we're going to do this with overall heat transfer coefficients. So basically, if we look at the gist of the temperature profile for a problem like this, since this is fixed at 25 degrees Celsius, this is known. We know in a solid it's linear. The temperature profile would look like that. And then with ambient, if it's 10 degrees Celsius out there or something, it would drop like that. Perhaps that was extreme. Maybe something like that. So basically, we have two different contributions to the thermal resistance, and it's very convenient to solve problems like this using the overall heat transfer coefficient, because this is known, temperature drop is known. So let's just go ahead and calculate U. So how can we calculate the overall heat transfer coefficient? Well, we can use this equation. For a planar surface, it's just going to be what is it going to be for a planar surface? We can calculate this using 1 over all of the ambient temperature, heat transfer coefficients, and then add in the resistance of generally this would be the sum of the resistances across solids like this. But we only have one surface, so I'm just going to call this 1 over R. And then R is defined as K over L. So what does this look like? It's going to be 1 over H plus L over K. We happen to know all those values for our situation. So 1 over U equals 1 over, what was H? 10 plus the length is 0.005. And then K, they told us, is 0.75. Let's do units on this too. Okay. Let's see, that's 1 over watts per meter squared Kelvin, and then this is meters, and then this is watts per meter Kelvin. So 1 over U is going to be 0.1 plus 0.005 divided by 0.75. So 1 over U is equal to 0.1067, we'll call it. And the meters here are going to be the inverse of this, which are going to be meters squared Kelvin over watts. And this one that's the same thing, obviously. And then when we inverse that, take the reciprocal, the overall heat transfer coefficient is going to be 9.37, and that's going to have the same units of H, of course. Okay, so now we have that. Now we basically have solved the problem. Throw it back into here. Let's calculate the heat, the total heat loss. So area, well, here, let's put in we'll do 9.37 watts per meter squared degree Kelvin. 1 meter squared for the area, and then our temperature drop is convert these to Kelvin. So 25 degrees Celsius plus 273. Why am I putting that in my calculator? We'll call it 298. And then 10 degrees Celsius is going to be 283. And so I just use this equation. Our total heat loss is going to be 9.37 times 1 times 298 minus 283. So 140.55. And then this unit, it was degrees Kelvin. So the units here, meters cancel, Kelvin cancel, and we're going to get watts, which makes sense. It should be watts. Heat loss, that's joules per second, so that should be watts. All right, and then that's not the answer they want. For the first part here, they want an annual cost, and they give us like a unit conversion. So they tell us 0.15 kilowatt hours, or $0.5 per kilowatt hour. So let's just convert this. This is equal to 0.141 kilowatts, we'll call it. Okay, and then let's see here. Okay, let's just apply our unit conversion. 0.141 kilowatts times this. Shoot. We're going to get 0.0211, and then let's see, our kilowatts cancel, and we're going to get dollars per hour. And then let's just convert that into, they want dollars per year. So, there's 24 hours in a day, 365 days in 1 year. So we take that number times by 24 times by 365, 184.7, we'll call it, dollars per day. Okay, so there's the answer to the first part. Let me check that. All right, looks good. Second part of the problem. Someone suggests a double glazed window. So we got 2 layers. Great drawing by me there. We have a double glazed window which consists of 2 panes of glass, each with a thickness 0.025 centimeters, and then they're separated by an air space. Okay. So we have air in here. And then these were, let's see, what were these? These were 0.25 centimeters, 0.0025 meters. Same thing. It's important to keep everything in SI units. And then what will be the savings in energy of this window? And then assume that the heat transferred across the space is only by conduction. Okay, so it's going to be linear, which means we're not going to use an H value. We're going to want to know just the K of air, which is, I have that value. Here, I'll write over here. K of air we will call 0.024. You can just look that number up if you didn't have it. And then essentially this is just like another solid. So now what we got to do is we just got to recalculate. We can still use this equation, the area times the overall heat transfer coefficient times delta T, where the other conditions are the same. So this is still 25 degrees Celsius. The area hasn't changed. This is still 10 degrees Celsius. We just got to recalculate the overall heat transfer coefficient. So same exact procedure as before. We still have, so here, let me redraw our temperature profile. So it drops a little bit here. Maybe it drops more there, some there, and then it does the ambient profile. So we have now 4 different things to add up in our overall heat transfer coefficient. So For solids, we did, in our equation, we did length over the thermal conductivity. So length, let's do this first one, 0.0025 over the thermal conductivity, which is in the problem, 0.75 for the glass. And then let's do the air. The air is, how thick is it? It's 1 millimeter thick, or 0.001 meters. We'll go ahead and throw that in there. And then we have another glass. And then we have our ambient portion, which they gave us heat transfer coefficient of 10, so 1 over 10. Okay, so if you can kind of follow here, this was 1, this was 2, this was 3, and then 4. Okay, so 1 over u is going to be equal to, let's throw this in the calculator. 0.1483, and then the overall heat transfer coefficient, if we take the reciprocal, 6.74, and that is watts per meter squared Kelvin. Okay, and then let's find the heat lost again. So same area as before. I'm going to omit units because I did them before. And then we have the same temperature difference. What was it, 298? Yeah, 298 minus 283. That's 15. Wait a second. Why did I... Okay. Okay. Times 0.674. So now our heat lost is 101 watts. And they want to know, what do they want to know? They want to know the savings. So if we were at 140 watts before, let's see, the easiest way to do this would just be to do like a ratio. So before we were at 140, right? Is that weird? Okay, I'll just call it 140.5. Since it's just a unit conversion, we can just like cheat a little bit and do this. Okay, so it's that ratio. And we know we were at how much money before? We were at $184.7. And if we just times that by the same ratio, we'll get how much it'll cost for this new value. I hope that made sense what I just did. Okay, so now it's going to cost about $132.9. So originally we had 184.7, and now we have 132.9. The difference is how much money we're saving, which is about $51.08. Okay, so then that would be how much we save for the double pane system. So here for this problem, the gist was we use Fourier's law to calculate the heat lost across this planar surface, and then we need to calculate the overall heat transfer coefficient, and then just multiply that by the temperature drop. So that's problem 10.1 from the book. Okay, this problem is pretty similar to 10.1. So we have a composite planar solid that consists of 2 panes of glass, each thickness 0.25 centimeters, or 0.025 meters, and they're separated by an airspace thickness 1 millimeter, or 0.01 meter. That's an airspace, so we'll do this. And they want us to assume that it goes across that space by conduction alone. and they want us to calculate the overall heat transfer coefficient for this system. So let's see, we're not given any H's from these ambient temperatures, so we're just going to assume that we know the temperature at the surface, and we're just going to consider the heat transfer coefficient from like this point, you know, in the temperature profile probably looks something like that, to there. So we're just going to look within the solids. So if you remember, we calculate overall heat transfer coefficients as 1 over the overall heat transfer coefficient equals, usually you add all of your convective transfers, which in our case we don't have any, so that's just not there. And then you add all the reciprocal of the resistances through solid materials, where R is just K over L. So for us, this is going to be, we'll do this, 1, 2, 3. So this is going to be L over K for 1 plus L over K for 2 plus L over K for 3. So 1 over U becomes 0.0025 meters over, let's see, they told us earlier, what is K of glass? K of glass, we're going to call 10. We're going to call K glass 10. They defined that in problem 10.1 because they were using the same materials. So 10, the length here is 0.001. The K of air for only conduction is, we also defined this earlier. Just looking for it. Oh, here we go. 0.024. 0.24 plus the same as the first term. Okay, let's calculate this 1 over heat transfer coefficient. Okay, so with the inside, considering, so the reciprocal of the overall heat transfer coefficient, considering that this is only conduction in that air part, we get 0.0421, and then that makes U 23.7 watts per meter squared Kelvin. Okay. And then that's the first of 3 parts. Or actually, it's the first of 2 parts. So now they want us to find the H. So now they want us to, instead, let me redraw the system. So let's say, now they want us to consider a system where this is convective. Our air is convective. So now the temperature profile might look something like, well, actually, I don't know what it'd look like. I don't know, something crazy, and then like a linear drop in the solid. And they want us to find the H for this, where it's equivalent to something. For what magnitude of convective heat transfer would the double pane system be thermally equivalent to a single pane thickness of 0.5 centimeters? Well, we should calculate that. So for a single pane of 0.5 centimeters, where K equals 10, the heat transfer coefficient would just be 0.005 over 10, which is just 0.0005, and then U becomes 2,000. Okay, so now we want to find the H that would make the overall heat transfer coefficient for this system within 1% of this system. So let's calculate, let's see what that equation would look like. So 1 over U is going to be equal to essentially 0.005 over 10. So 0.005. Yeah, 0.05 over 10. and then plus 1 over h. So now we have to include convective heat transfer. And we know that our overall heat transfer coefficient is going to get smaller because k is probably going to be a lower value. So let's decrease this number by 1%. So we're going to call this, what are we going to call this? We're going to take off 20. So 1,980. Sorry, it's late. So 1 over 1,980 equals 0.005 over 10 plus 1 over h. We're going to solve for h. So I'm going to do this value minus this value, which gets me this. So if we take the reciprocal of that number, we get h is a colossal number. Is that right? This is basically 198,000 for our h.